Hey there, this is problem set 35, where we're going to introduce the idea of enthalpy. And we say introduce the idea of enthalpy, really we're not introducing it because we've been dealing with enthalpies previously when we've been talking about heat capacities. We've been using enthalpies when describing the heat of a phase change, right? If you remember this equation, for example, this is calculating the heat associated with vaporizing something. So if I had delta H of vaporization of 40.7 kilojoules per mole, as water does, that means it takes 40.7 kilojoules to vaporize 1 mole. 40.7 kilojoules of heat to vaporize 1 mole. And then if I wanted to figure out how much total heat is involved, I have to multiply that by, let's say I was boiling 5 moles, that would give me 203.5 total kilojoules. So we see here that delta H that we've been using represents the amount of heat involved with performing a certain process, in this case, vaporization. But really now we're going to dive into what that enthalpy is. And to kind of understand why we're diving into it, we talked about how energy is heat plus work. We talked about how work is negative pressure times change in volume. We talked about how heat is either like an MC delta T equation, or it's an N delta H equation. And then now we're diving into what exactly is enthalpy. And that's why it falls at this point in the course, even though we've been using it in the past. So let's get into some of this. First off, we're going to define enthalpy. Enthalpy is the total energy in a system. Okay, and that's different. Well, that's different than internal energy. So internal energy is this E we've been talking about here. Change in internal energy is heat and work. So I would say energy includes all the internal energy, the kinetic energy, and the potential energy. Enthalpy is energy plus, we could say, the energy necessary to displace the environment. Let's write an equation and see if that makes more sense. So enthalpy is energy plus P times V. So we have your internal energy, and then you add to that the pressure required to stay at the volume that the system is at, and that gives you your your enthalpy. And that brings us to the question of when does delta H equal Q? And the answer to that is constant pressure, and I'll show you which this entire course is at constant pressure. So here's the idea why I'm talking about change in enthalpy. This is enthalpy, so change in enthalpy is delta H equals delta E plus delta PV, which is using the calculus chain rule, which you don't have to know. Oh man, you don't have to know, but you see if there's constant pressure, delta P is 0, so that's 0. And the other thing I need to add in here is to say we know that delta energy is Q plus W, which is the same as Q minus P delta V. So I can plug that in for E, and I get delta H equals Q minus P delta V plus P delta V. So this term was just replaced by that, which is right there. And you can see that those P delta V's will cancel, and I get delta H equals Q. Now the assumption we made here was that pressure was constant. Now that doesn't mean that numerically those numbers are always equal to each other, right? We saw over here, right, Q equals N times delta H. Well, that's just because this is like a unit heat, and this is a total heat. Right, so you still have to look at the units to see if delta H is your total amount of heat. Basically what this here is showing is that theoretically, if pressure is constant, enthalpy only includes heat change. If pressure wasn't constant, there would be other factors of the system that would be involved in calculating a change in enthalpy, but in this case, once you've calculated the total Q, you've calculated the total enthalpy change. So I could replace total heat and unit heat with total enthalpy and unit enthalpy. so because delta H is just heat when pressure is constant, we can answer a lot of the questions that we've previously answered about heat. So adding Drano to a clogged sink causes the drain pipe to get warm. What is the sign of delta H when it dissolves? Well, if it's causing the pipe, the surroundings, to get warm, that means that dissolving must be releasing heat. If it's releasing heat, then the sign of Q and the sign of delta H is negative. It's exothermic. Breaking a small pouch of water inside a chemical cold pack containing ammonium nitrate activates the pack, which is used by sports trainers for injured athletes. What is the sign of delta H for the process taking place in the cold pack? So you break a small pouch, and the whole thing gets cold. That means that whatever process is going on when you break that pouch is sucking heat in, so everything gets cold. Okay, and so what is the sign for delta H in this process? Well, if it's sucking in heat, it would be positive. And does delta H equal Q? Unless you're putting this pouch into a box that's changing pressure or something like that. But we don't do that in this class. In this class, delta H equals Q. We assume that pressure is constant. Okay, so now we want to calculate delta E and calculate delta H. So remember, delta H equals Q, delta E equals Q minus P delta V. So a sample of gas absorbs 25 kilojoules of heat. Bam, there's my heat. So I've already found what delta H is. I'm going to write over here, delta H equals 25 kilojoules of heat. Okay, and we can also use that here. So we have 25 kilojoules minus, and expands 25 liters against 1 atmosphere of pressure. Pressure is 1 atmosphere. It expands, so my change in volume is positive 25 liters. The problem here is these units don't make sense. This is kilojoules, and this is liter atmospheres. And so we're not able to just add those or subtract those, so we need to change these to make sure the units are the same. So I'm going to just write here, 1 liter atmosphere is 101.3 joules, and there's 1,000 joules in 1 kilojoule. So when I do that, the change in energy is 25 kilojoules. Let's do math real quick. This is like 2.5 kilojoules. So that leaves me with 22.5 kilojoules for the energy. Okay, sample of gas releases 9.2 kilojoules of heat. Well, there's my delta H. Also compresses from 30 liters to 5 liters under a constant pressure of 3 atmospheres. So change in energy is my heat. Oh, it releases, so that means it's going to be negative. So negative 9.2 kilojoules minus pressure. Change in volume. Change in volume is final minus initial. Again, the units are going to be messed up, so I'm going to change this to kilojoules, just like I did in the last one. And I get change in energy is going to be negative 9.2 kilojoules plus 7.6 kilojoules, which leaves me with negative 1.6. Hopefully you're starting to notice this pattern. A reaction releases 150 kilojoules of heat. Releases, so it's negative. And releases enough gaseous product to expand 275 liters from 5 liters against 2.5 atmospheres. So my change in energy is going to be my negative 150 kilojoules minus pressure. And change in volume. Going from, so final is 275 liters minus initial is 5 liters. Change in energy is negative 150 kilojoules minus 68.4 kilojoules, which leaves negative 218 kilojoules. Obviously, I'm not too worried about sig figs here. All right, a reaction absorbs 75 kilojoules of heat. It's a positive 75 kilojoules. This is enough gaseous product to expand 150 liters against an external pressure of 5 atmospheres. Change in energy is Q minus pressure. And it expands, so positive 150 liters. Here, delta E equals 75 kilojoules minus 76 kilojoules, which leaves me with a change in energy of negative 1 kilojoule. There you go. So that's, now we've done problems like this, similar to this before, but this is now trying to push the idea that we can refer to heat as just enthalpy as long as pressure is constant, which for our class it is. All right, so we've talked about how delta H refers to the heat associated with the process. So delta H of fusion, for example, refers to the heat associated with melting something or fusing, right? So we use subscripts to specify what process we're talking about. So delta H of vaporization is the heat involved with vaporize something. Delta H of fusion is the heat involved with melting. Delta H of a reaction is a more general term for the heat involved with any reaction. Delta H of formation is the heat involved with forming something. We'll talk about what a formation reaction is in a bit. And delta H of combustion is another one, which would be the heat involved with combusting something. Okay, and like I said, we will talk about these in a second. Usually they're in units of kilojoules per mole, so that you can decide how many moles I want to melt or something. But you could also have them in kilojoules per gram. There's nothing wrong with that. Okay. What's the difference between delta H of not of reaction and delta H of reaction? So really the question is, what does this mean? Okay, that tells you that we are at standard conditions, standard temperature and pressure, which for thermodynamics, standard temperature is 25 degrees Celsius, and standard pressure is 1 atmosphere. Now when we did gases, standard temperature was 0 degrees Celsius, and now it's 25, so something to keep in mind. Now this is just useful. You won't pay attention to it a lot, but sometimes you need to know the temperature at which something's happening, and they don't tell you the temperature, they just give you the naught. So that you would need to know that that's 25 degrees Celsius. Delta H of reaction just means, is again more general. This, because a reaction can happen at different temperatures, right? So this could be the reaction happening at inner temperature, this is the reaction happening at standard conditions. Explain Hess's law in your own words. And why or how it's so useful. Okay, Hess's law says because enthalpy is a state function, I can take any path I want to get, as long as I get from A to B using any path using any path I want. Okay, the enthalpies associated with the path that I take will add up to the enthalpies associated with the path directly from A to B. So let me maybe say that in better words. I'm trying to get from A to B. I want to know the delta H of that reaction. Okay, and maybe I don't know what it is, but I know the enthalpy change from getting from A to C and from C to B. Okay, so I'm trying to get A to B. I know A to C and C to B. Well, going from A to C and C to B is a different path, but the same result as going straight from A to B. So what that tells me is that in this case, this is delta H1, this is delta H2. A to B would have to be delta H1 plus delta H2. Now, maybe I didn't explain that very well, but we'll see examples later on. But that's really useful because there are certain paths that we know more about than other paths. So we can just pick the paths that we have information about to find information about paths we don't know. Okay, so we're going to use the information at the right to answer the following question. What is the enthalpy? Remember, enthalpy is just heat. Change when 100 grams of ice at negative 30 degrees Celsius is warmed to form water at 50 degrees Celsius. Okay, so I'm going to draw our little heat curve to see where we're going on this. Whoops. So we've got temperature on the left, we have heat on the bottom. We could also have delta H on the bottom, right? This is 0 degrees Celsius for water. This is the boiling point at 100 degrees Celsius. We've got 100 grams of ice starting at negative 30. So let's just say that is negative 30. And we want to end up at water at 50, right in the middle there. And we're trying to find the heat associated with that. Okay, so we're trying to find what is this Q, or this delta H, right? Again, I'm just writing them both because they are synonymous. Well, there's 3 processes going on to get from ice at negative 30 to water at 50. Okay, the first step is going to be to heat up my ice to its melting point. Okay, and in that case, I'm changing temperature, so that's going to be a Q equals mc delta T. Here I'm melting my ice. It's a phase change, so it's going to be Q equals m delta H of fusion. And then I've got to heat up my liquid, and so that's also a heat change, or a temperature change, so it's going to be Q equals mc delta T. Okay, and the total Q is going to be the sum of those 3 Qs. Okay, so we've just got to find each one individually. So we've got Q of our ice, Q of our melting, Q of our water. It's going to be M ice, C ice, delta T ice. It's going to be N melting, delta H, I should say fusion. This is going to be M water, C water, delta T water. Okay, so let's plug things in. I'm always going to look at the units on my C or my delta H to see what units I should use for other stuff. So my C value for ice is 2.03 joules per gram Kelvin. So I can use grams as my mass. Got 100 grams. My C is 2.03 joules per gram Kelvin. And my temperature change is from negative 30 up to 0. So 0 minus negative 30. So 30 degrees. Now, a lot of people ask here, they want to know, well, why do we use Celsius if that's in Kelvin? It's a good point. You're welcome to use Celsius, or you're welcome to use Kelvin. But what you'll see, because we're dealing with a change in temperature in Kelvin is the same as that change in temperature in Celsius. So this gives us a change in temperature of 30. If I were to convert my 0 to Kelvin, I would get 273. If I were to convert my negative 30 to Kelvin, I'd get 243. The difference between these is 30. The difference between these is 30. Okay, and so anytime you're dealing with a change, you're welcome to use Celsius or Kelvin. Do the math here. And I get 6090 joules. Right here, the units on my delta H of fusion are kilojoules per mole. Okay, so I need to use moles of water, not mass of water. So I'll just quickly change my 100 grams of water into moles. And that gives me 5.56 moles. So 5.56 moles. My delta H of fusion is 40.67 kilojoules per mole, which gives me 225.9 kilojoules. Okay, and then, oh, that's why that's weird. I used the wrong value. This is fusion. I should have used 6.01. There we go. That's more than I was expecting. 33.39 kilojoules. And now for this last water, my C value is in joules per gram, so I can use my 100 grams. 4.184 joules per gram Kelvin. My final temperature is 50, initial is 0. This gives me 20920 joules. Right now we want the total heat. We found the heat for the 3 steps, we just need to add them up. If we want to add them up, they need to be in the same units though. So I'm just going to change to kilojoules. You can change it to joules, doesn't matter. So the total Q, or total delta H, right, same things, is going to be 6.090 plus 33.39 plus 20.92. And I get total delta H of 60.4 kilojoules. Again, it wants the total enthalpy change. We just found the heat change, which is the same as the enthalpy change, total enthalpy change. All right, now we want to find the enthalpy change when 200 grams of steam is converted to 150 degrees C, or at 150 degrees C is converted to ice at negative 50. So let's draw our heat curve just to get an idea of what we're doing. Oh man, let me draw straight lines. So we're starting as steam at 150. I want to go to ice at negative 50. So how many steps do we get to take? We get to take 1, 2, 3, 4, 5. And really, should have gone this way. 1, 2, 3, 4, 5. Okay. So let's do it. We're going to start with our Q steam, cooling down our steam. Oh, I don't like black. Where's red? There we go. Q steam. Q condense. Q water. Q freeze. Q ice. This can be an M steam, C steam, delta T steam. This can be an N condensing, delta H condensing. This is going to be an M water, C water, delta T water. It's going to be a N freezing, delta H freezing. And this is going to be an M ice, C ice, delta T ice. Okay, 200 grams. My C value is, for steam, 1.84. I'm going from final of 100 minus 150. We get, and I'm just going to convert them all to kilojoules as I do this. So negative 18.4 kilojoules. Now we get a negative number. Does that make sense? It does, because I'm cooling down steam, so heat's going to be released. So it should be a negative value. Okay, here we've got our 200 grams, but we need it in moles. I'm going to divide by the molar mass right here. And now Q of condensation, sorry, delta H of condensation. They don't give us that. They give us delta H of vaporization. Vaporization is liquid to gas. Condensation is gas to liquid. And so it's going to be the same amount of heat, but it's going to be released instead of absorbed. So we're going to get negative 40.67. And there's no temperature change. There we go. we get negative 451 9 kilojoules. All right, we've got our 200 grams of water, 184 joules per gram Kelvin, and we're going ending at 0, starting at 100. Right, this whole line right there. And I get negative 83.68 kilojoules. Here we have our moles again, times 6.01, but it'll be negative 6.01 because I'm not melting, I'm freezing. That gives me a value of negative 66.8 kilojoules. And lastly, heat capacity of my ice is going to be 2.03. My ice is ending in negative 50, starting at 0. That gives me negative 20.3 kilojoules. Now I just want the whole heat from here all the way to there. So I just got to add them all up. And I add them all up. Negative 641 kilojoules. And we know it should be negative because heat would be released as I go from steam all the way down to ice. All right. Okay, number 6. A and B. Use the information about water above to answer the following questions. Watch your units. Refrigerators and freezers remove heat from food by evaporating volatile liquids such as CF4 and then recompressing the vapor back to a liquid. Okay. Calculate the mass of water at 0 degrees. It can be converted to ice at 0 degrees. So we are liquid at 0 degrees, converting to ice at 0 degrees. So this is 1, 2. What mass of water can be converted into ice when CF4 evaporates, when 100 grams of CF4 evaporates. So this is a situation where we've got heat transferring from our water into our CF4. CF4 is evaporating, right, and sucking heat out of the freezer, and that heat's coming from the water, which turns to ice. So we've got heat transferring between two different things. So I've got, what are my Q's? Q of CF4 plus Q of water, have to add up to 0. So I'm going to say Q of CF4 equals negative Q water. What's physically happening to my CF4? It's evaporating. That's a phase change. So I'm going to have N CF4 delta H of vaporization of CF4 equals negative. What's happening to my water? It's freezing. So N water delta H freezing of water. If they tell me how much CF4 I have, they tell me the delta H of vaporization of CF4. So I've got this side of the equation. Let's plug those in. So I've got 136 kilojoules per kilogram, my delta H vaporization, and I've got 100 grams, so I'm going to change that to kilograms so that the units work. Now this side of the equation is kilojoules. Equals negative. I'm looking for my amount of water, so I need the delta H of freezing of water. Well, they give me the delta H of fusion, which is melting, so freezing is the opposite, so negative 6.01. So this side of the equation, kilojoules per multimole, gives me kilojoules. So my units work, so I'm welcome to go ahead and do math. And when I do that, I get there you go. I get and water equals 2.26 moles, but they want the mass, so I got to convert that to grams. I'm going to do that, and I get the mass of water equals 40.7 grams. So if I evaporate 100 grams of CF4, the heat that absorbs is the same heat as it takes to freeze 40.7 grams of water. Okay, similar problem. Water in a leather flask or a porous clay pot can be cooled in hot climates by evaporating water from the surface of the container. So we've got our pot, it's got water in it, and we put water on the outside, right? And that water evaporates, and when it evaporates, it takes heat from the water inside. Right, and so that will cool down the water on the inside. So water in a leather flask or a porous clay pot can be cooled in hot climates by evaporating water from the surface of the container. Calculate the mass of what mass of water can be cooled from 35 to 20 would be the evaporation of 60 grams of water. Okay, so we've got heat transferring between two things. So I've got Q of my vaporizing water plus Q of my, I'll just say the water on the inside, equals 0. So what's happening to the water that's vaporizing? Well, it's vaporizing, so I'll have N vape, delta H vape, goes negative. What's happening to the water on the inside? It's getting colder. So I've got the mass of the water, C of the water, the delta T of the water. So we're evaporating 60 grams of water, and we're going to use a delta H of vaporization. Delta H of vaporization is 40.67 kilojoules per mole. Okay. And then how much am I vaporizing? 60 grams. I need that in moles, so I'll just divide by 18. Equals negative. The mass of my water on the inside, that's what I'm looking for. How much mass, how much water could I cool down? Got 4.184 joules per gram degrees Celsius, and my temperature changes from 35 to 20, so 20 degrees Celsius minus 35 degrees Celsius. Now if we look at the units, on the left side we'll have kilojoules, but on the right side we'll have joules. So to change that, I can quickly just add here. I want to get to kilojoules. There's 1,000 joules in 1 kilojoule. Okay, so let's plug it in. When I do that, I get the mass of my water is going to be 2160 grams of water. Okay, if you get a negative amount for the mass, it probably just meant that you forgot to add this negative sign, or that you did your temperature changes the wrong direction, right? It should be final minus initial. Okay, we want to calculate the delta H for this reaction using the information below. Now this is an example of Hess's law that we talked about previously. Basically what we're going to do is we're going to use these equations, and if we can get these equations to add up to this one, then these delta H's will add up to the delta H of this. So let's go through that real quickly. The easiest way to learn how to do this is just to see how it's done. So I want or I should say this, there's two things I can do to these equations. One, I can flip them. Two, I can scale them. Okay, and so you'll see how we do that. So here, I want C2H4 on the left. I want one of them. Well, in these equations, I don't have any C2H4 on the left, but I have one on the right. So I'm going to flip that equation. C2H4 goes to 2 carbons plus 2H2. And now I don't care about this equation anymore. I care about this one that I've written, which is going to have, if this process going forward has a delta H of 52.3 kilojoules, then the process going backward would have a delta H of negative 52.3 kilojoules. So that's the new one I care about. Okay, C2H4 is good. I need 6 F2s. Well, I've got F2s, but they're in 2 different spots. I don't know which one to manipulate, so I'm just going to skip it for now and see if it fixes itself as I manipulate other things. 2 CF4s on the right. I've got 1 CF4 on the right, so let's scale that equation. Let's multiply the whole thing by 2. When I double that equation, the delta H of that equation is now going to double as well. Now this one's good. Okay, my 2 CF4s are ready. Now I've got my 4 HFs. I've got 2 there, so I've got to scale that equation. I double the delta H as well, and I get negative 1074, I believe. And you can see now I needed my 6 F2s. Now I've got my 6 F2s on the left. So they took care of themselves as I manipulated other things. Okay, so now we got to check. Let's check, because why we were doing this is to get these 3 equations to add up to that guy. So let's see if it does. I'm going to write all my reactants going to all my products. C2H4 plus 2 carbon plus 4F2 plus 2H2 plus another 2 fluorines, so 6 F2 goes to 2 carbons plus 2H2 plus 2 CF4 plus 4HF. Well, anything that's on both sides, I don't care about. So I can get rid of that, get rid of that. I can get rid of this, get rid of this. And that leaves me with C2H4 plus 6F2 goes to 2CF4 plus 4HF. And I want to know the delta H of this reaction. You can see that is the same as that. Well, because these equations add up to this equation, Hess's law tells us that these delta H's will add up to this delta H. So we can literally just add them up now. And I get negative 2486.3 kilojoules. There you have it. That is how Hess's law works. All right, number 8, last one. The enthalpy of combustion for graphite is negative 393.5. All right, enthalpy of combustion for graphite. So what equation is that for? That's for C graphite plus O2 goes to CO2. The delta H of that reaction is the delta H of combustion of graphite, because this reaction is the combustion of graphite. So those 2 things are just synonymous in this case. And that equals negative 393.5 kilojoules per mole of graphite. The enthalpy of combustion for diamond is C diamond plus O2 goes to CO2. The delta H of that reaction is the delta H of combustion of diamond. That's negative 395.4 kilojoules per mole. use this information and Hess's law to calculate the delta H of the reaction converting diamond to graphite. I shouldn't put these in parentheses because they're not phases. Here we go. I'm trying to get the delta H of this reaction. And is that endo or exothermic? Okay, well, let's use Hess's law. I need diamond on the left. I've got it. I need carbon on the, or I need graphite on the right. I don't have it. It's on the left. So let's get it. Let's flip that equation. When I flip that equation, I've got to flip the delta H. Now it's no longer the delta H of combustion of graphite because this is not the combustion reaction of graphite, it's the opposite. Now let's check these add up to each other. Well, I've got my diamond on the left, graphite on the right, so we're good. And everything else has to cancel. O2 on the left cancels O2 on the right. CO2 on the left cancels CO2 on the right. So I've confirmed that these equations add up to that equation, and as a result, these delta H's will add up to this delta H. Which gives me negative 1.9 kilojoules per mole. There you go. So that must be exothermic because the delta H is negative. All right, so here we've been introduced to conceptually to enthalpy, and we have used it in aspect of heat, which covers some of the stuff we've already done with some heat equations. Okay, and we've also now learned how to use Hess's law. Hess's law is one way to calculate the enthalpy of a reaction. There are two other ways which we will hit on problem set 35.